All right, guys. In this lesson, we're going to be looking at exponential functions and their graphs. And we got somewhat introduced to this in the M&M and dice activity, and we're going to build off of that today. So from your packet, you should have the basic exponential equation is y equals a times b to the x, okay? And in this equation, a cannot be 0. Otherwise, it would multiply out, the whole thing would be 0. We wouldn't have an exponential. B cannot be 1 because if b were 1, then it wouldn't grow or decay, and b also has to be a positive value, so it's going to be greater than 0. A is like our A1 value equivalent. It's going to be the initial value of the function, and if there are no transformations, it will also act as our y-intercept. B is going to be our growth or decay factor. It's like our common ratio from a geometric sequence. In order for it to be exponential growth, the b value needs to be greater than 1. And if it were to be decay, then the b value needs to be less than 1. But again, we know it needs to be positive, so we're going to say it needs to be between 0 and 1 for decay. Below we can see just kind of a recap of arithmetic and geometric sequences and comparing them to linear functions and exponential functions. So an arithmetic sequence compares pretty directly to a linear function. And in that, in order to, when we move from one x value to the next, we're going to add the slope each time. And we know that linear functions or arithmetic sequences will grow by a constant value. So we would say add 5 each time to go from one term to the next. With an exponential function or a geometric sequence, you're going to instead multiply by the b value each time that x increases by 1. We say that exponential functions are going to grow by a constant rate. So maybe they increase by 5% each time, okay? Looking at a general linear function, we know what those look like. Might just look something like that. We know it goes in the general mx plus b form. And an exponential equation is going to start out growing slowly and eventually start to grow very quickly, okay, in our a times b to the x form. In order for us to be working with an exponential function, this sounds obvious, but it's easy to miss sometimes. In order for us to be working with an exponential function, the variable itself needs to be in the exponent, okay? So if we have the variable elsewhere, if x is elsewhere, then it's not exponential, okay? It needs to be in the exponent. We're going to go below and try a few practice problems here, okay? We're going to determine if these are exponentials, and if they are, what do we know about them? There are a few that are a little bit tricky, but I want you guys to pause the video and try these yourself right now, go through them, and then come back and play it, and I'll walk through the rest of it. So for the first one, we've got f of x equals 2 to the x power. Okay, this is kind of a classic basic exponential function. So is this exponential? Yes. In this case, our a value is 1 because there's nothing out in front of that 2, right? The 2 is going to be our b value because it's getting raised to the x power. And with nothing else there, a is 1. We're going to consider this to be exponential growth. And careful here, this is a little confusing. It's actually growing at a 100% growth rate, not 200%, because you can essentially do it as that b value minus 1 is going to be our rate of growth. So 2 minus 1 will get 100%. The next one, we have 4x to the negative second power. This one is not exponential because we have a negative 2 in our exponent rather than an x value. The third one, negative 3 times 2.6 to the x. This is exponential. And in this case, our A value is -3. Our B value is 2.6. And this is going to be exponential growth, and it's going to be growing by 160%. Again, 2.6 minus 1 times 100%. The fourth one here is a little bit tricky because of this -x, okay? With the x still in the exponent, it will be exponential, but it's going to change a few things. It's essentially going to reflect our graph over the y-axis, and it's going to change it from being exponential growth to actually exponential decay because of that reflection. So our A value is going to be 10. Our B value, I'm actually going to take the reciprocal of 6, and it's going to be 1/6. And as a result, that's going to be exponential decay. And I'm going to do 1 minus 1/6 would be 5/6, or as a percent, about 83% decay rate, okay? That one's a little confusing. Don't get too caught up on it right now. We'll have a chance to go over more like that in the future. And then the last one, f of x equals 2 times 5 to the e power. In this case, we're raised to the e power. We'll learn about the term e in our next lesson, but it's actually not a variable. It's kind of like pi. It's representing a number. And because of that, this is not going to be an exponential equation. We would need the x in that exponent, okay? We'll go to the next page, and here, again, I want you guys to try to work through this yourself. So I want you to go through everything from 1a up until you hit the exponential graphs section, okay? So pause the video, go ahead and try to write out an equation for those, and they won't all be exponential, and then come back and you can look through what I find. So for 1a, we've got a population is initially 100 and increases by 5 people each year. Well, that's just going to be linear growth, okay? Because we're just adding a fixed value. So I can think of that as being y is equal to 100 plus 5x, increases by 5 per year. 1b, the population is initially 100 and it increases by 5% per year, is instead going to be exponential, right? So that's going to be 100 times 1.05 is going to be our b value to the x power. Number 2, we've got the depreciating car. So our initial value is going to be $30,000. And because it's losing 22% per year, we're going to subtract that from 1. And our b value is going to be 0.78, and then to the x power. Number 3, the value of the wine is appreciating, meaning it's increasing in this case by 10% each year. So this is going to be exponential again, and we're going to have exponential growth this time. So 10% plus 1, so 1.1 to the x. The fourth one, with the M&Ms, that's going to be linear, right? We start with 800 and we take out 10 each day. Number 5, we're looking at the inflation rate here. And we initially have a cost of 2.09, and we want to see how that's going to change in X years given a 1.5% inflation rate. So 2.09 will be A, and then 1.015 because of 1.5% being added to 1 to the X. That'll be our equation. And then in the long run, exponential functions will always grow faster than linear equations, okay? Down below, we're going to introduce exponential graphs. And a fundamental part of an exponential graph is what we call a horizontal asymptote. You can see on here that an asymptote is basically showing what the end behavior of the graph is going to do in one direction, okay? The graph is going to approach this line, and it's going to get closer and closer to it, but it will not reach it, okay? And when we have exponential graphs, we'll always be dealing with horizontal asymptotes. So every exponential graph will have one horizontal asymptote on it. If there are no transformations to it, we're going to find that asymptote at y equals 0. Again, y equals 0, remember y equals a number, denotes that we're using a horizontal line. And for exponential functions, the graph will either grow away from the asymptote if it is exponential growth, or it will decay towards the asymptote if it is decay. Be careful on this. It doesn't just mean that if the graph goes up, it's growth, and if it goes down, it's decay. Okay? We really want to think of it in terms of, does it move towards the asymptote or does it move away from the asymptote? And we can look at some examples of this below with these 4 different graphs. So in this first one, the equation of our asymptote, and asymptotes can kind of be represented on a graph with just a dotted line. So I can see, all right, we've got this line at y equals 0 is going to be our asymptote in this case. And because it's moving towards the asymptote, this is going to be decay. For our end behavior, we're stating what happens in both directions, right? So in this case, as x approaches infinity, as we move to the right, notice that y actually approaches 0. I believe this is our first time seeing it where it doesn't approach infinity in one direction. When we go to the left, in this case, to negative infinity, this time y will go to positive infinity. Okay? Looking at the next one, in this case, again, our asymptote is going to be on the axis, okay, and it's going to again be y equals 0. This time this is going to be exponential growth, though, because we're moving away, okay? So even though it's going down, this is still growth. It moves away from the asymptote. It just means that we have a negative a value causing this to go downwards. Our end behavior here, as x approaches infinity, y is going to approach negative infinity, and as x approaches negative infinity, as we move to the left, y is going to approach 0. Okay? Pause the video here and try the next 2, and then go ahead and play it once you've given them a try. On the third one, we have a shift here that's actually moving our asymptote down by 2. So that's going to be at y equals negative 2. This is going to be growth because, again, it's moving away from the asymptote in this case. As x approaches infinity, y approaches infinity. And as x approaches negative infinity, y will approach negative 2. It will approach the asymptote. Okay, our last one. Here, the asymptote is going to be at y equals 2. And this is going to be decay because it's, even though it's increasing, it's moving towards the asymptote. So that'll be decay. Again, it just means we have a negative a value. As x approaches infinity, y is going to approach 2. And as x approaches negative infinity, y will approach negative infinity. Okay. Down onto the next page, we're going to start looking at creating our own graphs for an exponential function. Okay. One of the key things to understand when we're graphing anything, and I've said this all year, is that if you don't know what a graph looks like, just plug in points, make an x and y chart. Okay. And that's just what we'll do with this. We just want to figure out useful x and y values to plug in, and that will help us build our graph. Oftentimes, if there aren't any transformations to it, we'll like to start around 0 and move a little bit in each direction to fill things in. Okay, so let's take a look through these examples here. Our first one is y equals 2 to the x power. Okay, this is going to be an example of exponential growth because our b value is 2. Okay, I'm not actually going to make a table, but I'll talk through the points that we would be using. I'll start at an x value of 0. Okay, so that's going to be 2 to the 0th power is 1. All right, so our y-intercept is actually going to be at 1. Notice that our a value in this case is also 1. If I start moving to the right, 2 to the first power is going to be 2. 2 to the second power will be 4. And 2 to the third power will be 8. So we see this growing at an increasing rate. Notice that as we go from one term to the next, we are multiplying that y value by 2, or multiplying it by the b value. Now I can also go in the negative direction here, okay? And if I did 2 to the negative first power, that would be 1 over 2, so we would have a value of 1/2, okay? 2 to the negative second power would be 1 over 2 squared, so 1/4. 2 to the negative third would be 1/8, and you can see us approaching the asymptote for this graph at 0. So it flattens out, and then since it's growth, it's going to move away from the asymptote, and it's going to grow over time. Okay? Notice I've got arrows going in both directions. The domain for any exponential function, okay, you can go ahead and fill this in for all of these here, is going to be all real numbers, okay? It's always going to be negative infinity to infinity for the domain. The range, well, our minimum value is going to be approaching 0. It's not going to actually reach 0, so I'll use a parentheses for our minimum, 0, and then it's going to approach infinity, okay? So 0 to infinity. Next one, y equals 10 times 1/2 to the x. In this case, we are dealing with exponential decay because of our b value being less than 1. Again, I'm just going to plug in points for x and make my graph from there. So let's start at 0, okay? 1/2 to the 0 power is 1 times 10 is 10. So our y-intercept is going to be that a value of 10. As I move to the right, so then x value of 1, 10 times 1/2 to the first will be 5. 10 times 1/2 to the second, so 1/2 squared is 1/4. That's going to give us 2.5. 10 times 1/2 cubed will be what? 1.25, and so on. Again, this is going to approach 0, right? That's where our asymptote is for this graph, so it's going to approach 0. Now, if I moved in the other direction, if I tried an x value of -1, what are we going to see here? Well, 1/2 to the negative first power is going to do a reciprocal, so it's going to give us 2 times 10 will be 20, okay? So notice as you're moving to the right on this graph that you are multiplying by 1/2 to go from one term to the next, okay? We know our domain, and our range is actually going to be the same. Even though this graph looks pretty different, it's still 0 to infinity in this case. Okay. Third one is another example of exponential growth, but I notice on this one, our a value is negative. That negative a value is going to cause us to reflect over the x-axis. Okay, so this is going to go downwards. But I'll still use that same general process of just picking x values, plugging them in, and getting my graph. Okay, so if I start at 0, 1.5 to the 0 is 1 times -2 is -2. If I go to the right, 1.5 to the first times -2 will be -3. Then 1.5 squared would be, 2.25 times -2 is going to be -4. And so on, right? If you want, you can use your calculator for this to help you find like 3, 4, 5 values for it. If I go to the left, okay, to the negative first power, so 1.5 to the negative first power times -2 should give me, can't think of the value off the top of my head. I've got it on my chart as about -1.5 roughly. And we're going to see again that our asymptote is at 0. And we are showing exponential growth, and just going down in this case because of the negative a value reflecting. Okay? For the last one here, I actually want to go down and fill in this part first. Okay? So in our in our basic exponential function, a times b to the x, we know that our starting value and our y-intercept is a, as we saw on these examples. Our growth or decay factor is b, and we're going to find our asymptote at 0. But as with any function, we can see plenty of transformations that can occur to it. And we're going to see a, h, and k show up as they've shown up in all of our other functions that we've worked with this year. Remember that h means that we are going to have a horizontal shift. So if we're moving left or right, that's going to be based on the h value. And if we're moving up or down, that's going to be based on the k value. Remember, h is always inside the function, so it has to be attached to the x. So it's going to be in the exponent. K is outside the function, so it's going to be just added at the end. The rate of growth or decay you can think of as the b value, or we talked earlier about how you can just add it or subtract it from 1. Okay, so the difference from that and 1 is the rate of growth or decay. Our asymptote is going to be based on any vertical shifts here. So it's going to be based on the k value. So the asymptote will be whatever k is in any given case. Okay? With that in mind, let's go look at this last one up top. On this one, we're going to be dealing with exponential growth again. Okay, but we see some transformations here. Okay, I see we're shifted 2 to the left and that we're shifted up by 1. Well, that shift up 1 is going to tell us our asymptote is at 1. So I know we're starting there and going up. Okay. Again, I can just pick some points to plug in. This time, rather than starting in an x value of 0, I might start by making my exponent itself equal to 0, meaning that I might start with an x value of negative 2. And if I do that, then it's going to be 3 to the 0th is 1 times 2 plus 1 would give us 3 as our starting point there. If I move to the right, if I plug in negative 1 for x, that gives me an exponent of positive 1. And that's going to give us an output of 7. If I plug in 0 for x, it's going to give us an exponent of 2. And that's going to give us an output of 19. And then if I move to the left, again, this is going to start just getting closer and closer to the asymptote. So if I plugged in negative 3 in that case, that's going to be 2/3 plus 1, so about 1 2/3. So about right there. And so on. And we're going to see that it's going to get closer to that asymptote if we were to plug in additional points. Okay? Let's see, I missed my domain for the last one, and range. Our range there is going to be negative infinity to 0, lowest to highest, remember. And then on this one, our domain, again, all real numbers. And our range this time, the lowest value is going to be 1 up to infinity, okay, because that's where our asymptote is. Last thing that I want to go through in this is the reverse, which is working through when we're given a graph, finding an equation for it, okay? So we're going to start with a given function, and then the other two are going to be transformations to that function. So let's start with the first one and see if we can figure out what that is, okay? I see that we've got a y-intercept at 6. Okay, and so assuming no other modifications to this, I'm going to say that our a value is 6. And as I go from one term to the next, so as I go from negative 1 to 0, as I go from 0 to 1, what's happening to the y value? Well, what's happening to the y value is that we are multiplying it by 1/3. Okay, 18 times 1/3 is 6, 6 times 1/3 is 2, and so on. So this is going to give us our basic function to start with here. We're going to see transformations on these next two, okay? So when I look at the second graph, I notice that it's got the same basic shape, but this time it's been shifted, okay? So what I could do is I could look for some comparison points for myself if I wanted to. So like if that's our reference point, this seems to be our equivalent point there. And so we moved up by 2 and right by 4, okay? Let's say if I looked at another reference point, we had 1, 2 on our initial graph. Again, here we go up by 2 and we go right by 4. Okay, so our new transformation is going to be 6 times 1/3 to the x minus 4, since we're shifted 4 to the right, and then plus 2. And you can notice that our asymptote in this case is going to be at y equals 2, right? That's where it flattens to. Our last one here, it still has the same basic shape, except this time it's been reflected, right? So rather than starting at 0, 6, we're starting at 0, negative 6. Rather than being at 1, 2, we're at 1, negative 2. What that's telling me is that we've just been reflected, and so our a value just needs to be flipped. So I could say we've got y equals -6 times 1/3 to the x power. Okay. And that's what I wanted to cover in this lesson. The rest of the stuff, I'll have you work on part of it for homework. But that's it for this. Remember to like, comment, and subscribe. Have a good day.